Hey, chemistry classes, second through fifth hour. I'm going to quickly go through this Unit 3, Worksheet 3. Things that you probably did last year if you took physical science, but it's worth reviewing. We've dealt with this formula already that Q, which is heat, is equal to M times C times delta T, which means mass times specific heat times delta T. But oftentimes you're not always asking for heat. Sometimes you have to figure out the mass or the specific heat or the change in temp or the final temp or the initial temp. So we're going to need to be able to rearrange algebraically that formula. Some of us, if we struggle at algebra, there's a little shortcut some people use called a round, or in this case, oval little buddy. If you used this last year, it's a way of setting up an equation. The Q would go on top, and then the M and the C and the delta T go on the bottom. If Q, heat, is equal to M times C times delta T, if I cover up, how do I cover up? If I cover up Q, it's going to tell me that I have to multiply M times C times delta T. That'll be a little bit of a challenge because I can't cover it up. So if we're going to rearrange these formulas, Q equals MC delta T, what if I needed to find mass? How would I do that? I'd cover up mass, and I would see Q on the top divided by C times the change in temperature, C times delta T. I need to get my M back there. What if I needed to find C, which is specific heat? If I crossed off or covered up C, Q again would be on top, the heat would go on top, divided by mass times delta T. So it's telling me where they go multiplication or division wise. What, I need to get my C back there. What if I needed delta T, the change in temp? To get the change in temp, I would have Q on top, heat on top, divided by M times C. Oftentimes they don't want to know the change. They want to know the final temp or the initial temp. Well, the final temp, if we just rearrange, change in temp just means the final temp. Change in temp equals final temp minus initial or original temp. So rearranging these formulas, final temp would simply be the initial temperature plus the change in temp. An initial temp would be temp final minus the change in temp. So we could use those. It's just using math to rearrange some stuff. Here's another little review, something called dimensional analysis. Mr. Knapp showed a couple in the example, so I won't deal with those. Here's the way I'd explain it. Here's a fact. 2.2 pounds is 1 kilogram. If I have 20 pounds, how many kilograms? Well, 20 pounds. I like to put it over 1 because that way I can tell it's at the top of the fraction. Here's a fact. 2.2 pounds is 1 kilogram. I don't want pounds anymore, so put pounds on the bottom. We'll get the numbers later. What I really need to know is kilograms, so I'll put that on top. Now go get the numbers. Pounds has a 2.2 next to it, so put a 2.2. 20, let's see, kilograms has a 1 next to it. What this means is 20 divided by 2.2 because I don't have to put it into a fraction. 20 divided by 2.2, and my answer would be 9.1 after rounding. 9.1 kilograms or 9.1. What about another one? 35 kilograms. How many pounds is that? Well, they told me I'm starting with kilograms. I like to put it over 1. I don't want kilograms, so put it on the bottom. What I need is pounds. Now go get the numbers. Pounds has a 2.2 next to it. That goes on top. Kilograms has a 1 next to it. That goes on the bottom. This one is 35 times 2.2 equals 77 kilograms, and kilograms cross off. Pounds is at 77. Relationship between grams and kilograms. 1,000 grams equals 1 kilogram, and 1 kilogram equals 1,000 grams. What if you started with 4,500 grams? How many kilograms is that? Well, if some of you who get confused doing it in your head, realize that grams has to go on the bottom and kilograms has to go on top. So that way, grams and grams will cross off, leaving us kilograms. But now we need the numbers. Kilograms has a 1 next to it. Grams has 1,000 next to it. 4,500 divided by 1,000 is like moving the decimal over 3. It's 4.5 kilograms. 35 kilograms equals how many grams? Well, if we have 35 kilograms, I like to put it over 1, and 1 kilogram is equal to 1,000 grams, then I just multiply 35 times 1,000 to get 35,000 grams. How did I know where to put the 1 kilogram? I set it up in such a way that kilograms would cross off, grams would stay there, then I simply matched the number that was necessary. So let's go on to the next ones. We're going to be using some of these down here, and as you can see, Mr. Knapp did not round this off. I don't know. We'll see where I'm at. I'll probably just use the one that he said. We'll see. For each of the problems, sketch a warming or cooling curve to help you decide which equations to use. Please show your work with the units, your work, and the answer. I start with my cooling curve. A cup of coffee cools from 75 down to 20. That seems pretty easy. 75 degrees Celsius down to 20. That's just simply one step. It's not a 5-step or 4-stepper. It's just one step. There's not even a phase change. How much energy does it release to the surroundings? How much energy? Remember that Q equals M times C times delta T. So this is a pretty straightforward one. Mass in this case, 140 grams. Specific heat. Coffee is mostly made of water, so we're going to use the same specific heat as liquid water, 4.18. 4.18 joules per gram degrees Celsius. Change in temp from 75 to 20 is 55 degrees Celsius. Put all that into the calculator, and we should get about 32,186. What's that, you ask? What would be the unit? Well, grams and grams, degrees Celsius, all crossed off. Joules would be our answer. Suppose during volleyball practice you lost 2 pounds of water due to sweating. If all this water evaporated, how much did the water absorb from your body? Said we had to draw a heating or cooling curve. How do I do that? It's not even a temperature, but it tells me what it did. It evaporated. Now this is a tough one because things can evaporate without boiling. Boiling's just the magic number that makes it that there's enough heat to make it evaporate rapidly, but it's an evaporation sort of thing, so we're going to need a heat of that vaporization. 2 pounds of water. Express your answer in kilojoules. Let's see. Well, we haven't done anything with kilojoules. All we've done is joules. So what do we got? All I know how to do is do this in joules. And so what I'm going to do is change it in such a way that I can keep using the same formula so that I can do it in joules. Then I'll rethink this idea. First things first, I have 2.2 pounds. And I don't want pounds. What I want is grams. But I don't have anything about grams. I only have a relationship between pounds and kilograms. So I'm going to set it up in such a way that pounds cross off and kilograms stay there. Here's the fact. 1 kilogram is 2.2 pounds. All that would let me do is cross off pounds and leave me kilograms. I don't want kilograms, so what I'm going to do is I'm going to put kilograms on the bottom and grams at the top. What's the relationship between grams and kilogram? 1 kilogram is 1,000 grams. So into my calculator, I did something wrong here. This should have been a 2.0. I'm sorry about that. 2.0 pounds. 2.0 times 1,000 because it's on the top, divided by 2.2, and I ignore all those other things. I'm getting 909 or 909.1 grams. I'm just going to say 909 grams. Okay, what am I really after? How much energy did the water absorb? So in this case, there is no change in temp, so Q equals MC delta T isn't going to help us. What is going to help us is It's evaporating. Heat of vaporization evaporating is 2260 joules per gram. So when I go back to this one, 909 grams times 2260 joules per gram. Get my calculator. 909 times 2260 equals, egads, I see why they wanted it in kilojoules, equals, and I'm going to write it down here, 2054350. Let me double check that. All right, that was a 40. That is joules. I'm going to put that over 1. I don't want it in joules. I want it in kilojoules. Kilo just means, or kilo just means 1,000. Kilojoules means 1,000 joules. 1,000 joules is 1 kilojoule. So all I really have to do is move the decimal over. 2054340 divided by 1,000. 1, 2, 3. I'm going to put that as 2054.3 kilojoules. And you may have gotten something slightly different depending on if you rounded like I did, but something in that ballpark. So exact figures aren't always that necessary because a slight little rounding back there would have made that difference. On to the next one. Suppose that during the icy hot lab, I didn't call it that, but that's when we heated up ice and we watched the temperature and then we kept heating it and recorded the graph. 65 kilojoules of energy were transferred to 450 grams of water at 20 degrees Celsius. What would have been the final temp of the water? Okay, let me just remind you. I'm going to just get my round little buddy back out here. Q, M times C times delta T. The thing that I'm after is going to be the final temp. Well, there's no final temp on here, but what I'm going to try to figure out is the change in temp, and then I can do some thinking and figure out what the final temp. 65 kilojoules of energy. I could go through the math and do this. See, here's the problem. All of these things, all these calculations we've been dealing with have been in joules and grams, and when we start mixing the kilo into there, we might just want to convert those right off the get-go. 65 kilojoules is 65,000 joules of energy. So Q is 65,000 joules divided by mass is 450 grams. Divided also, and I'm going to write it as a times, it's confusing to people, but the specific heat of, we are talking about 20 degrees Celsius, water, so that's liquid, so it's 4.18 joules per gram degrees Celsius. How would I put that into the calculator? This will confuse some of you, unless you like to use parentheses, but I don't. I'm going to take the number on top, 65,000, divided it by 450, because 450 is on the bottom, and I'm also going to divide it by 4.18. Even though I wrote times, I'm not using parentheses, so I'm simply going to divide it, and I'm going to get equals 34.6. It's a little tough to see that joules and joules cross off, and grams cross off, and since this is on the bottom of the fraction and gets divided, it ends up being degrees Celsius. I know that's tough to see. These are tougher than we'll need to have. Probably a product of me not being here right now. What would have been the final temp of the water? Is it 34.6? No. This 34.6 is not the final. It is the change in temperature. We started with 20. And we transferred energy, which means it's going to warm up, and it's going to change by 34.6. 20 degrees Celsius plus 34.6 equals 54.6 degrees Celsius. That is our final. On to the next one. The heat capacity, or C, specific heat, of solid iron is 0.447 joules per gram degree Celsius. Same quantity of energy that was in number 3 were transferred to a 450 gram chunk of iron. What would be the final temp? Okay, it's another one where I'm after the final temp, and since there is no final temp, I'm really shooting for change in temp first. So it's however much heat divided by mass divided by specific heat. Let's see, let's do the ones I don't have to switch pages for. 450 grams is the mass. Specific heat is, well, it's iron, and they're telling us it's 0.447 joules per grams times degrees Celsius. Let me go back to number 3 to get that same amount of heat. That amount of heat was, well, 65,000 joules. 65,000 joules. Handy dandy calculator. 65,000 divided by 450 and also divided by 0.447. That's going to be a change in temperature of 323 degrees Celsius. That's a change in temp, though. That's what I was solving for, a change in temp. Change in temp. So in this case, since it started at 20 and it changed by 323, 323 plus 20 degrees Celsius is 343 degrees Celsius. I think this is the point they're trying to make. 450 gram chunk, add 65,000 joules, it was 20 degrees Celsius, it'll get 343 degrees Celsius. That's really, really hot. You would be permanently scarred if you touched it. But water only gets up to 54.6. It's the same amount of heat, same amount of temperature, but since the specific heat of water is so much higher, it can absorb a lot more heat without change in temp. On to 5, bag full of ice, 450 grams, a 0. Sits on the counter and begins to melt to liquid. How much energy must be absorbed by the ice if 2/3 of it is melted? Bag full of ice is at 0, and it's not even going to get any warmer because only 2/3 of it is going to melt. Wait a minute. We had 450 grams times 2/3 of that. Looks to me like only 300 grams is going to melt. How much heat does it take to melt 300 grams of water? 300 grams. This is where I'm going to have to probably use a different, no it's not. How much heat does it take to melt water? That's the heat of fusion, melting or freezing. 334 joules per gram. 300 times 334 joules per gram. 300 times 334. 100,200. That would be grams and grams, joules of energy. Serving of Cheez-Its releases 130. They're changing stuff on us. 130 kilocalories. 1 kilocal equals 4.18 joules. Let's just turn it into joules because that's what we do best. And that's what all of our heat of fusions, heat of vaporizations, and all that stuff are in. If we have 130 kilocalories, and let's see, kilocalories goes on the bottom, and kilojoules goes on top. Kilocalories has a 1 next to it. This has a 4.18 next to it. But we don't want kilojoules. So 1 kilojoule is equal to 1,000 joules. That'll cross off. This dimensional analysis lets me not have to know much about these numbers. I just arrange things in such a way that I can cross off what I don't need and keep what I need. 130 times 4.18 times 1,000, 543,400. 543,400 joules. Final temp. This is going to be a, let's see, Q, M, C, delta T. I can't figure out a final temp from here. All I can do is a change in temp. Heat on top, mass and specific heat on the bottom. How much heat? 5, 4, wait, I could just do it right here. Heat on top, specific heat, what are we dealing with? Water. At 27 degrees Celsius, so that's liquid water. So specific heat is 4.18 joules per gram degrees Celsius. How much water are we dealing with? 2.5 kilograms, which is 2,500 grams, because a kilogram is just 1,000 grams. 543,400 is already showing. divided by 2500 divided by 4.18. That's going to equal 52. That's going to equal degrees Celsius, but that's not the final temp. That's the change in temp. These Cheez-Its are released into your body when they're digested, so they're going to add heat to your body. If they were adding the same amount of energy to water, that was 27 degrees Celsius plus 52 would equal 79 degrees Celsius. If this same quantity of energy, which was 543,400, were transferred to 2.5 kilograms of water, at its boiling point, what fraction of the water would be vaporized? Do we really go for that one? Fraction of the water. Well, there's nowhere on this Q equals MC delta T that's going to be the fraction of the water. But we're going to need to know the mass of the water so we can figure out how much of it actually was boiled away. So we're shooting for the mass